Hello again, AP Physics students. In today's lesson, we're going to continue to look at situations where we want to figure out the electric field due to an object that has a continuous charge distribution. But once again, we'll be faced with a scenario where we cannot apply Gauss's law, which is going to require, much like in the previous lesson, a little bit more work in setting things up so we can perform an integration in which we can figure out what the electric field is. In the last lesson, what we specifically looked at is we had a finite length of wire with a continuous charge distribution. And the primary difference between that lesson and this one is instead of having a finite straight length of wire, we're going to have that wire bent a little bit. So specifically, we're going to bend it so it's going to be in the shape of a circular arc. If you look at the diagram here, it kind of illustrates the context of the problem. So we have a positive uniform charge density identified by lambda, and it's bent into an arc that has a radius of r. If you did fully extend the arc, it would fill in a complete circle. The arc is placed so it centers at the origin, and we want to figure out what the electric field is at the center of the arc. And we'll do it based on those angles that we see in the question there. Okay, so first step, much like you're going to see a lot of similarities between like how we kind of set things up in the previous lesson and this one. The first thing we want to do is we just want to identify what the direction is of the electric field at point O. Once again, that's pretty easy to do because you just have, you can use symmetrical arguments to like figure out what it is. So for example, if I were to draw just a couple of these positive charges on here, so one here and one there, one here and then one there. And if we drew the electric field at point O due to these charges, well, right here, you'd have like a component that would point somewhere like down like that. Okay, from this one, you'd have a component that points something up like this. And you can see immediately that just the vertical components cancel off. And it'd be much the same if I were to draw the electric field vectors due to this charge and this charge. So we can immediately identify just due to symmetrical arguments that the electric field, the net electric field due to that curved arc of wire is going to be towards the right. And the reason being is because the y components cancel off. So therefore at position O, we can just draw an electric field vector that points towards the right. Okay, now step two, because we're dealing with a circle, in terms of identifying the different positions on that curved rod, it's not really practical to do that in terms of x and y coordinates. The better way to identify a specific position on the rod is going to be with an angle. Now, in order to identify an angle, we have to establish what we want to be the reference axis. And once we have the reference axis established, then we can identify like where does the rod start and where does the curved section of the rod end at. So as I mentioned, the first thing you want to do is you want to choose an appropriate reference axis to measure the angle for where your arc of charge is going to start and where your arc of charge is going to end. What you want to do is you want to move counterclockwise to the arc, and you want to try to sweep through as small of an angle as possible. So immediately, some people might be thinking, let's just make the positive x-axis the reference axis. But in general, what I want to do is I want to choose a reference axis so that the angle between the reference axis and where the arc of charge starts is going to be the smallest angle possible. Now, if I'm going in a counterclockwise direction, if I start the positive x-axis, that's too big of an angle to go through. So the better axis to start at in terms of it dealing with a reference axis is we're going to make the positive y-axis the reference axis. And then that's going to have a smaller angle from the reference axis to where this arc of charge is going to start. And then we're going to just identify the angle based on where does the rod start and where does the rod end. And we're going to use those as lower and upper limits of integration a little bit later on in this problem. So if we do this, we're going to say my reference angle is the positive y-axis. So the reference axis, that's where theta would be equal to 0 degrees. We're going to call the angle from the reference axis counterclockwise to where the arc of charge starts as theta L. So theta L just represents the lower limit of the rod, which is just the angle from the reference axis to where the arc of charge is going to start off. And then we're going to call theta U the angle from the reference axis to where the rod of charge is going to end at. Okay, and I call it theta U for upper limit because as you see later on, we're going to use that as a limit of integration when we start to integrate to figure out what the total charge is. So in this particular example, I believe the angle between, if you just go back to the, well, I don't need to go back to the picture. I can just simply just identify this with a diagram here. So if we just grab and make this red, okay. Yeah, so this angle right here was 60 degrees. Okay, this angle right here was also 60 degrees. Therefore, your lower limit of integration, your lower angle here, theta L, would just be 90 minus 60, which is 30. And then the upper one would be, you just add 60 degrees to this quadrant. So from this y-axis to the negative x-axis would be 90, add 60 degrees to that, and then you would have 150 degrees. So that's going to identify the position where the arc of charge starts and where the arc of charge ends. And again, it's much better to do this in terms of an angle as opposed to identifying x and y coordinates. It would be like an absolute nightmare to deal with in this problem. Now, step 3 is we're going to take the total arc of charge and we're going to break it into into a bunch of like really tiny chunks of charge. So this entire arc of charge has an arc length, which we're going to identify by the variable s. And that entire arc of charge contains a total charge that is, we'll call capital Q. And we're going to take that total arc and we're going to break it into a bunch of incrementally small sections of arc length. And we're going to call that delta S. Each one of these differential arc length sections is going to have a differential charge that's going to be delta Q. So again, if we go back to the picture, this entire arc of charge has a total arc length of S, and it contains a total charge of Q. We're going to take a very small chunk of that arc. That's what I'm using to represent this red chunk here. Now, obviously, the differential arc length would be like much smaller than what I have in the picture, but just for illustration purposes, we just want to be able to see what one of these chunks looks like. So that little red chunk of the arc would have an arc length of delta S, and the amount of charge in it would be delta Q. What we're going to do is we're going to try to write an expression for what delta Q is in terms of the incrementally small arc length. And then we'll just change it to calculus notation where we write it as a differential relationship as opposed to being in terms of delta S. So we can do a ratio between the variables we see on the picture. So if you take the total charge in the full arc of charge you have there, and you divide by delta Q, which is the charge contained in that differential arc length, that small chunk of the arc length, that would be equivalent to the total arc length divided by the arc length of that differential element. And if we manipulate the equation for delta Q, we then have delta Q is equal to Q divided by S times delta S. Well, we can actually rewrite the Q divided by S in terms of a variable that's given in the problem. This would technically be the linear charge density, because if you were to take that arc and you're just to pull it, straighten it out, you could straighten the arc out into a straight line. So we can represent that with a linear charge density. So therefore, we have lambda, which would be equal to Q over S, which then gives me an equation that would be delta Q is equal to lambda times S. But I want to write this in differential notation. So instead of like delta, we're going to represent it with D. Therefore, I have an equation that tells me the amount of charge contained in one of these differential arc lengths would be equal to lambda, which is the linear charge density, multiplied by the arc length of one of these differential elements. Now, what I want to do now is I want to take that differential arc length and I want to relate it to the angle that is being swept by that differential element. So you have to remember the way in which we're setting up the problem is we've already identified that we're going to have a lower limit of I think it was 30 degrees and an upper limit of 150. Those are angles. So what I have to try to do is I need to write ds so it's in terms of theta because that's what I'm going to have to integrate with respect to theta because that's what the upper and lower limits of integration are. Okay, now I'm going to draw a line that just starts from the origin and it goes to just where the beginning of that differential arc length section. Okay, then moving in a direction that's counterclockwise. So this position here would be where the differential arc length starts. And if we go counterclockwise, this is where the differential arc length is going to end. The angle that you sweep in going from where the differential arc length starts to where the differential arc length ends, we're going to call that d theta. Okay. So d theta is the angle that is essentially just covered by the angle swept by this differential arc length. Now, to get an equation from this, we have an equation that relates, and this is also from Math 30-1 as well, but this is on the Physics C formula sheet. So if we have the radius is r, we're assuming right here that the actual thickness of the arc of charge is like pretty small. So I've shown the radius as being from the center here to like just the inside radius, but let's assume that like this thickness right here is actually really small. So in which case r is just going to be the radius just to where the arc length of charge is going to be. So on the formula sheet, we have this relationship. Your arc length is equal to your radius times theta. Now, in this particular problem, we're representing the radius with capital R as opposed to little r. So we have S is equal to R times d theta. Now, that would be for the entire arc of charge. But again, I want to do it just for this little tiny differential arc length. So if we turn that into differential notation, we can just write it like this. So for this differential, this little chunk of the arc length, delta S, that would be equivalent to the radius multiplied by the angle swept by that differential arc length, which would just be delta theta. If we write that in calculus notation, okay, differential notation, we then have ds is equal to capital R times d theta. So going back to the equation on the previous slide, we identified that dq is equal to lambda times ds. And now we have an equation for ds in terms of d theta. So just take this equation and plug it in here. And then we have an equation that tells me dq is equal to lambda times r times d theta. So again, I'm just doing some prep work that's going to allow me to integrate when I'm required to put all the differential arc lengths back together. Now, step 6. So we're going to say theta represents the angle from the reference axis to the differential element. And what I want to now do is I want to write down an expression for what is the magnitude of the electric field at point O due to this differential arc length, which contains a differential amount of charge, which is dq. So again, theta is just the angle from the reference axis to where that differential element exists. Now you have to remember this differential element actually has like an infinitely small arc length. So realistically speaking, there's not much difference between the angle from the y-axis here to where the arc of charge starts compared to the y-axis to where the arc of charge is going to end. Okay, this differential arc length is actually really, really tiny. So if we were to represent what the electric field would be just due to this red chunk, well, if you put a positive test charge at the origin, then a positive test charge would want to repel away from this positive. Again, we had a linear charge density was positive, so it wants to repel away from that differential arc length. So it's going to be some direction that's going to be down and towards the right. Now, again, if we look at the equation for what the electric field is due to a point charge, and we did this last time, so the magnitude of the electric field due to a point charge is kq over r squared. If we look at the electric field due to an incrementally small chunk of this wire, which contains an incrementally small amount of charge dq, we can just take the electric field equation and write it like this. So dE would be the electric field due to that differential element of charge, and that would be equal to Q times dQ, because dQ is the charge within this red little chunk here, and then divide that by r squared. And again, we're using capital R instead of little r because that's how it's defined in terms of in the context of the problem. And now we have dE is equal to k dQ over r squared. Well, we know from the previous slide that dQ is equal to lambda times capital R times d theta. So I'm just going to take this equation here for dQ and sub it into the equation for dE. And if you do that, you would then have dE is equal to k over r squared multiplied by lambda times capital R times d theta. And as you can see here, there's this r on the top and this exponent 2 are just going to cancel off, which would then leave you with an equation that tells you dE is equal to k times lambda over capital R and then multiplied by d theta. So that's the electric field due to this incremental, this differential arc length section at point O in terms of d theta. Now, step 7, that's the electric field only due to that single chunk of the total arc of that of this full arc length that we have here. So we want this for the entire arc of charge, not just for this tiny little arc length, this red arc length we have here. Going back to step 1, we already identified that the only thing that matters is the x component of this electric field. All the y components are going to cancel off. Therefore, there's no point of actually looking at them whatsoever. So we're going to take this electric field vector. Again, technically you should have a vector sign on top of here, but we'll just leave it as dE for now. And then, so we have dE that points somewhere down and towards the right. Now, I'm going to show the vector components on this. So we'll draw a vector component DEY that points straight down and a vector component DEX that points towards the right. Typically, I like to draw the X component first, then the Y component second. But the reason I do it in this manner here is because it makes it a bit more clear. If you look at this, the direction of this vector, and you want to compare it to this angle theta that you have up in this quadrant, it makes it much more clear what the angle theta is. So it turns out this angle theta between the y-axis and the differential arc length of charge is equivalent to this angle in the top corner here. So now we can write an equation for what dEx is, because dEx is the only thing I'm interested in, because it's only the x components that are going to contribute to the total electric field at the end. Yeah, and again, this angle right here is relative to the y-axis in this problem. So yeah, just be careful. Typically, when we do like a components calculation, usually it's the x component is cos and the y component is sine. But just based on the way I've drawn the triangle here, this angle is relative to the y-axis. So again, now we're going to figure out what the magnitude of the electric field is at point O due to dQ, only in the x direction, because that's what matters when we find out the total. So we can write down dEx would be equal to dE times sine of theta. From the previous slide, we had an equation for what dE was, and that equation was dE is k lambda over capital R times d theta times sine theta. And we can just write it like this now. We have dEx is equal to k times lambda times sine of theta over R multiplied by d theta. Okay, so that's going to be the electric field due to this small chunk of the arc length at point O in the x direction. But again, we want this for the entire arc of charge that we have. So step 8 is now we just integrate. So we're going to integrate both sides of the equation, and we're going to do that over the entire arc of the rod. So that's going to put all the differential elements back together. So d theta is an indication we're going to integrate with respect to theta. And again, we initially identified my upper and lower limits of integration were going to be angles because that's the easiest way to define the position of where the arc starts and ends. So that's why we had to do all this prep work to try to get an equation for dE in terms of d theta, because theta is going to be the variable I have to integrate with respect to. And then that's what we'll do in the example problem on the next slide here. We'll just figure out what this integral is going to be equal to. Okay, so going back here, so this again was an old AP question, a part of it anyways. So again, now it gives us some numbers. We have a rod of uniform linear charge density, lambda, which is positive, 1.5 times 10 to the negative 5 coulombs per meter. It's bent into an arc that has a radius of capital R, 0.10 meters. And again, the arc is placed so it centers at the origin. And we want to figure out two things. I want the total charge of the rod, and I also want to figure out what is the magnitude and direction of the electric field at the center. Well, let's do part B first, just because we've already done all the work to get like this equation. And then we'll just figure out what the electric field is, and we'll go back and figure out what part A is, although you easily could do part A first. But I just want to kind of just continue moving with the direction we were going in trying to figure out what the total electric field is, because that was my original intent. Okay, so the way we do this is we're going to take this equation. The left-hand side of the equation, we're going to integrate from 0 to your total electric field. And so we're going to integrate dEx from 0 to E. And then that's going to be equal to, we're going to integrate the right-hand side of the equation from the angle where the arc of charge starts. So relative to that positive y-axis, that's a 30-degree angle. And then we're going to stop where the rod of charge is going to end. Okay. So this is basically telling you we're going to consider every differential arc element starting from 30 degrees and going all the way to 150, which gives me the total electric field at the end. Okay, we're going to integrate this equation. So we have K times lambda times sine of theta. And then we have divided by R, and we're going to integrate that with respect to theta. Oops, just made a slight error there. So let me quickly erase that. Now, before I integrate, I can pull out anything that's constant. So K can be pulled out of the equation, the linear charge density can be pulled out, and the radius of the circle is obviously constant. So the left-hand side of the equation just integrate to being E, which is your total electric field, because it would just be E minus 0. And then this would be equal to K multiplied by lambda, all divided by R. And we're going to integrate that from 30 degrees to 150 degrees. And we're going to integrate, find the antiderivative of sine of theta, and we're going to integrate that with respect to d theta. Now, the antiderivative of sine of theta would be negative cosine of theta. So this would be equal to K times lambda over R, and then negative cosine of theta. And we're going to evaluate that antiderivative from a lower limit of 30 degrees to an upper limit that's going to be 150 degrees. Again, if you're ever not sure if you do these antiderivatives correctly, you can always just find the derivative and see if you can get back to where you started. So the derivative of cosine is negative sine. So that would just be a negative times negative sine, and that would just leave you with sine of theta again. Okay, that negative, I can pull it out. Doesn't have to be there. So let's just grab the negative sign and pull it out before we evaluate. So again, you can always pull constants out. One before you find the antiderivative, and two before you evaluate it. So this would then just be equal to, so let's go back here. We would have this being equal to negative K times lambda and then all divided by capital R. And then we're just going to plug in cos of theta, the upper limit, minus cos of theta, the lower limit. So we have cosine of 150 degrees, and we're going to subtract cosine of 30 degrees. Okay, so your electric field would then be equal to, let's plug all the numbers in. So this would be negative. So we have Coulomb's constant. We'll use the value that's on the physics C formula sheet. So that's the two significant digits, 9.0 times 10 to the 9 newtons times meters squared per coulomb squared. And then we're going to multiply by the linear charge density. That's given to me as positive 1.5 times 10 to the negative 5. And we have coulombs per meter. And then we're going to divide this by capital R, which is the radius of this arc of charge, and that's 0.10 meters. Okay, multiply this by cosine of 150. I don't need to write down what these values are off the unit circle because I'm just doing a calculation anyways. We can plug this all into our calculator. So multiply by cosine of 30 degrees. And then we'll just identify both the magnitude and the direction in one step. So you would have E. I'll put a, oops, I don't know what just happened there. I got some like horizontal line that mystically appeared. Oh, I erased the wrong thing. Sorry, the fraction here went away. Okay, here, let's try to fix that. Okay, and then this would be equal to, you'd have E would be equal to, let's put the vector sign on top. It would be 2.3 times 10 to the power of 6. And the units are newtons per coulomb. And as identified at the start of the problem, we identified with symmetrical arguments that the electric field is towards the right. So that is my solution to part B. Okay, so this is B. Now, we skipped over part A. We'll come back to it now. So what part A wanted me to do is it just says figure out what the total charge on the rod is. Okay, here's the idea behind this. So your linear charge density, if this was just like a straight line of charge, your linear charge density would just be Q divided by capital L, where capital L is just the length of the wire or the rod, whatever we're looking at here. Now, for an arc of charge, instead of length, we're going to write it down as arc length. So we just have lambda would be equal to Q divided by S. So if I want to figure out what Q is for the entire rod, I just have to go Q, and that would be equal to lambda times S. Okay, here's a bit of logic in how you can do this. So if this was a full circle, so 360 degrees, that would be a full circle. And if you did have a full circle, then your arc length would just be equal to the circumference of the circle. So that would just be equal to 2 pi times r. Now, if we go back to the picture here, so what, compared to like the angle for a full circle, which is 360, what angle does this arc of charge sweep? It's 120 degrees. So for 120 degrees, okay, that's the angle covered by this arc of charge. That would be a third of the circle. 1/3 of full circle. So what the arc length would be is the arc length would just be the circumference divided by 3. So the total arc length would just be 2/3 pi r. Okay, so now we're just going to plug this into the equation here. So we would have Q would then be equal to your linear charge density and then multiply by 2 pi r divided by 3. Okay, let's plug the numbers into this equation. So this would be the linear charge density is positive 1.5 times 10 to the, I got that horizontal line going on there again. Not that it's a big deal. We can just ignore it if it happens again. Positive 1.5 times 10 to the negative 5 coulombs per meter. And then we're going to multiply by 2 over 3 times pi, and then times the radius, which is 0.10 meters. I close the bracket off, and then we get my total charge on this bent wire, or this arc of charge, is going to be positive 3.1 times 10 to the negative 6 coulombs. So again, this is a scenario where you just can't apply Gauss's law because, again, like trying to draw a Gaussian surface where you could have nice symmetry, where you would have like the electric field constant on every differential area element dA, and the angle between dA and the electric field the same at every single position is just not going to happen. So in these situations, you have to resort to like more of a procedure like this. And aside from the fact that we were dealing with arc length just compared to like an actual linear length, I mean, arc length is just like a linear length. You can just take the arc and just straighten it out. The procedure is like very similar, except the main difference in this problem was that it was better to identify the position of the wire in terms of angles, which required a bit more work and writing everything in terms of theta. All right, so in assignment number 8, you can complete, I think there's just one question dealing with the electric field at the center of a circular arc of charge, and I'll talk to you in the next lesson.